Okay, so we'll just go through mostly tutorial 4 and pick some of the calculation questions from tutorial 5. But most of tutorial 5 is like conceptual questions that it's better off you go home and think about them. And yeah, it's unlikely for those to pop out in exams, kind of like food for thought kind of thing. Okay, but in tutorial 4, let's start with just question 1. So you need to consider a quantum gas in a room roughly the size of G31 and roughly the same number, density, and temperature. And you have to estimate the energy levels. So, okay, G31, I'm going to say it's about 5 meter cubed. I think that's not too crazy. I think that, yeah, I think it's about 2 meters by 6 meters by like, I don't know, 10 meters. Or something of that magnitude. But yeah, let's just consider it to be 5 meter cubed. So then the length of the room, G31, is about 5 meters. And consider just that room temperature, so T equals 300 Kelvin. And now, so in that room, we can easily, if it's just a monatomic gas, then we can estimate the average energy inside that room for the particles. So at room temperature, you only excite 3 degrees of freedom, so you just get 3½ kT from equipartition theorem. And if we plug in the numbers, this is approximately, let's just call it 5 times 10 to the minus 21 joules for the average energy. And I think in one of the previous tutorials when we consider room temperature air, we just assumed everything's nitrogen. So let's do that again. So in this case, the mass of a nitrogen molecule, so N2, is approximately, I found this on Google, so I don't know how correct that is. It's about 5 times 10 to the minus 26 kilograms. Yeah, okay. So that's the context. And then now for calculating actual energy levels, we're considering a room that's roughly like cubic in size. So if we consider the energy levels from like quantum mechanics, energy levels in a cubic potential. So yeah, recall from, I don't know, 30 QM, epsilon n. So the nth level energy is equal to n squared, pi squared, h bar squared on 2ml squared. So yeah, that's derived from quantum mechanics. I'm not going to go through it here. But yeah, if we quote this for the energy level for the nth level, we plug in the mass of the nitrogen molecule and the length of our potential, which is the room here. Then you get approximately 5 times 10 to the minus 44 n squared joules. So you plug in whatever energy level n you care about, and that's how much energy is corresponding to that level n. So since we know in this room, the average energy is about that, so we want to find which n corresponds to this average energy. So just equating this epsilon n to this average E, epsilon n to average E, we get epsilon n equals angle brackets E, so that's approximately n squared is equal to 1 times 10 to the 23. So that's the average energy level of the average particle that will occupy. The problem now is to find the degeneracy of this energy level. So like how many degeneracies, like how many n's can we, nx, ny's, and nz's. So if you don't remember, in a cubic potential, this n squared is technically defined as n squared is equal to nx squared plus ny squared plus nz squared. So it's like 3 1D potential. So now we have to ask for the degeneracy levels that what combinations of nx, ny, and nz give us this n squared. And as you can probably guess, there's going to be a lot of them. So the best way to estimate the degeneracy is to consider a 3D like phase space sort of thing. It's not quite phase space, but consider 3 axes. So you have nx, ny, and nz. So this 3-dimensional space, as you're moving along, you're incrementing up by 1 to like integers to essentially move up in the energy levels. And the convenient part about thinking about it this way is that n squared equals nx squared plus ny squared plus nz squared. This just defines the, like this n is just represents as the radius of some circle centered at the origin of this nx, ny, and z space. So if we want to find for a fixed n squared, how many of these combinations we can have, you can consider a quarter circle and find the surface area. Surface area of quarter circle of radius n. Because if you fix the radius n, then you know every point on the surface of this circle, the three coordinates nx, ny, and z must satisfy this equation. Yep, question?
Sorry, so would nx, ny, and z be strictly integer here, or it can be any positive number?
They're strictly integers, positive integers.
Yeah.
So the surface area trick only really works for like n very large. So if n is enormous, which in this case it is, then when you get there, like the integer spacings are small enough that you can kind of approximate them as like a continuum. Yeah. So yeah, so to find how many degeneracies, we simply now find the surface area. So area is just 4 pi r squared. So in this case, degeneracy g for n equals 1 times 10 to the, n squared equals 1 times 10 to the 23 is equal to 4 pi n squared. So that's approximately, I think it was 1.57 times 10 to the 23. So there's a lot of different combinations you can have that will give you this n. Okay, and part B, harder, and yeah, it was actually pretty hard. The sparsity of the occupied states. So it's actually saying if this is the, if we have some distribution of our energy states, so this is our like n, and you got some distribution of the energy states. If this is like the average, how far do we have to go? Like how far in n do we have to go to find the next occupied state? Or how far in energy do we have to go to find the next occupied n state? So let me get an eraser. Okay, so what you do know is that the total number of microstates or total number of states within some energy shell is given by the density of state times by the thickness of that energy shell. So in this case, if we think about how many, the density of state in here, where rho is defined as the n, the epsilon, where n is the total number of states that we have. So the total number of states is rather than surface area, it's the volume. So the volume enclosed by some maximum energy level is going to be the total number of states allowed within those energies. So this can be, the rho in this case can be written as V on 4 pi squared h bar squared, or cube, sorry, h bar cubed, 2m to the 3/2 times epsilon to the half. So basically, that just comes from integrating the volume and then differentiating it. So plugging that into there, then your total number of microstates within that energy level is V on 4 pi squared h bar cubed 2n to the 3/2. Oh, sorry, there's 3/2 on the outside. Epsilon to the half, the epsilon. Okay, so if I integrate this from some energy, so say epsilon n to, just write in the next line so it's not so messy. So if I integrate this expression, so omega as a function of energy, from some energy epsilon n to epsilon m plus delta, where delta is like, I moved from epsilon to a slightly higher energy level at epsilon m plus delta level. And I want to know within this shell of energy, how many states exist in there. So this will just be the epsilon, so integrate over that. And if I integrate this will give me like a number of states within this delta shell. And if I equate this to the number of degenerate states there, so g n squared equals 1 times 10 to the 23. So that gives you, equating this to a number of states in this shell, gives me like an estimate saying if I start around the average energy and I try to cramp all of the states around it, how far do I have to like kind of go before I can add any more states? So it's like, how many can I fit around this? And if you go slightly further out and you can fit more, then you should know that, okay, we've reached the like energy level where you can find the next n. So that gives you like a rough estimate of what's going on. Yeah, so in this case, then you just integrate this expression, then you get something like v on 4 pi squared h bar cubed 2m to the 3/2 2/3 epsilon n plus delta to the power of 3/2 minus epsilon n to the power of 3/2. And this whole expression equals 1.5 times 10 to the plus 23. Yeah, so in this equation, we technically know everything. We know the mass, that's the nitrogen molecule mass. We know the volume is 25 meter cubed. And we know the epsilon n, because we're assuming this is the average energy, the average E. So the only thing we have to solve for is just this delta to find how like wide this shell have to be to fit all those states in. And if you work it out, the numbers get like completely ridiculous. My calculator refused to do it the first time. So your volume is approximately, eventually we get epsilon plus delta, epsilon n plus delta to the power of 3/2 minus epsilon n to the power of 3/2 is approximately 1 times 10 to the minus 73. And epsilon n, as we estimated before, is about 5 times 10 to the minus 21. So in comparison, this is like a huge number compared to that. So if I try to actually solve this for delta, I'm just going to get 0 because the calculator, at least the calculator I have, pretend like this number doesn't even exist. So you can kind of fudge this. Okay, delta has to be somewhere around like 1 times 10 to the minus 73 because the scales are just so far apart that there's no way for you to actually numerically get an estimate for it. But yeah, the main point of this is not the numbers because we basically rounded off these numbers every step we went. So it's not going to be a precise measurement, but it just tells you that the sparsity is very tight. It's tiny. And that large, every state is basically right next to each other. And that kind of like validates our assumption before that you can assume n forms a continuum to integrate or like to calculate surface area. Okay, so that was like a question 1. Cool. Then we'll move on to question 3. So not this one, question 3. Actually, do you want me to do question 2? It's about a Stirling approximation. Are you guys comfortable with that? Yeah, it's not that interesting. Like the answers are there anyway, so yeah, I'll just skip it. But if we have time, I'll come back to it. It's just like basically crunching through algebra. Question 3 is a bit more interesting. So question 3 for tutorial 4 says show that a spin system, part A, show that for a spin system is capable of achieving negative and infinite temperature. So how does that work? So for a spin system, the energy is related to the magnetic field, so m mu b, where m is like the number of spin states that are like difference between the spin up and spin down states. So yeah, if you this is our answer from question 2, but still, you can work out the entropy quite easy. So entropy is k log omega, and for the spin state, you can write this log omega. So let's write the whole entropy as k n log n minus k n on 2 minus e on 2 mu b log 2 minus 2 mu b. So these are just results from a Stirling approximation. Minus k n on 2 Yeah. So if you go through the last question, you'll get this. It's and I think it's in your lecture notes as well. So it's from a Stirling approximation, and so this is your entropy S, and we define a temperature, 1 on temperature, as ds du, or in this case, internal energy is just energy, so we just call it ds dE instead. So we just have to differentiate this expression with respect to energy. And only these terms will contribute, and because it's been log terms, you're going to get some pretty simple expressions. So ds dE is going to be k on 2 mu b log of, you're going to combine a couple of these terms together, but it's just algebra, m mu b minus e divided by n mu b plus e. So this is the expression for 1 over temperature. And now we just have to consider, okay, what happens if we take the limit where energy goes to 0 and for 1 over t. So basically this expression, then you just get k on 2 mu b log of 1. These two e's disappear and the rest of it just cancel out. So log of 1 will just kill this thing, so it just comes to 0. So it approaches 0 from above. But then your 1 on t goes to, if 1 on t goes to 0 and in the limit e going to 0, then that tells me that t is going to go to infinity. So if you reduce the energy in a magnetic system to 0, then you're going to get a divergent temperature. Yeah, okay, I'll keep this up on top. And for the next ones to see, okay, how does negative temperature work? So in a magnetic system, at least as far as I understand, the way that you define energy is like a relative energy. Relative energy. So it depends on whether your spin is like defined as a spin up or spin down. You have one like 0 energy level is defined where everything is like the spins cancel out. So you have the net spin down. If you define spin up as a positive energy, then you have a net spin down in all of your spins. So say like 1 up, 2 up, down, 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 down. You got more spin down than spin up. Then the total energy, E, in this case, is kind of like defined to be an actual absolute negative value. So you have a negative energy in this magnetic system. Only because you set the reference 0 point energy somewhere arbitrary. But if you have negative energy, then from the same expression that we had before, 1 over t equals k on 2 mu b, the log term now gets flipped. So rather than n mu b minus e, you're going to get n mu b plus e divided by n mu b minus e. So it looks almost the same as above, except you flip the signs in the numerator and denominator. And you can, of course, flip that again with just the log laws. 2 mu b log of n mu b minus e divided by n mu b plus e. And now if I take the limit where the absolute energy goes to 0 of 1 over t, then this equals 0 but approaches from below instead. So you still get log 1 in here when you take e to 0, but difference between that is that that approaches 0 from above, this approaches it from below. So that means that t actually goes to negative infinity when you take when you have a negative relative energy. So that's how you get like a negative temperature. Not quite sure what the deep implications are. Okay, part B. Illustrate that any system with a bounded phase space is capable of negative temperatures. So a bounded phase space means you have some max energy. So phase space is like your P versus X kind of space. So there's some, you can allow some like spatial freedom, but then the momentum upper bound would mean that you're bounded by some maximum kinetic energy. So if you consider this as your phase space, so you got some like X on the horizontal axis and your momentum on the Y axis, or energy, kind of like related concepts, then you can imagine you have this upper bound on this box. So you can sit in the ground state here, your particles, all these spatial ground states, and as they gain more like energy or heat, they start jumping up, but there's an upper limit on where they can jump. Whereas in a real system, or like not real, like in a free system, then as you inject more energy, they'll just climb up to higher and higher energy levels, but not for this case. You actually like, you have to be stopped at somewhere. So if you consider this the ground state, then from just looking at it, you have a fairly ordered collection ensemble of particles. So you have low energy as well as low entropy. Now, if I start injecting energy, inject E into this ensemble, then some of them will jump up to high energy systems. So some of them will still ground state, some of them might be higher, some even higher. Let's just assume they've kind of got some distribution like that. So here you have like medium amounts of energy, like not the most, because these lower ones can still be pushed up more if you gave them more energy. So you got some medium levels of energy, but you have like very high entropy. Things kind of are flying everywhere. There's not a lot of order to be had here. But now if I consider, I keep injecting more energy to give this as much energy as possible, where ultimately what's going to happen is that all of the particles are going to end up on this upper bound energy state. So they can't take any more energy and they all just fly to the top and they're not allowed to go any higher. So now I have an extreme high amount of energy, but I have low entropy again. Everything's kind of sitting in like a reverse to ground state. So now everything's kind of ordered. So if you consider the definition for temperature and is d energy or du normally, but in this case energy is E, ds, then we see for the first part, as energy increases, entropy increases. So then this is a positive gradient. So then temperature is positive because it's
going up as it's a positive gradient. But for the second half of the case, as I increase temperature further, my entropy starts decreasing. So in this case, this gradient of temperature versus entropy is going to be a negative gradient. And that being negative would tell me that I now have a negative temperature. So that's basically what it means to have a negative temperature in a bounded phase space system. And this leads on quite easily into the next part where, where's the questions? For part C, you want to say, given the intuition for temperature, are negative temperature very hot or very cold? So intuitively, if we consider like a hot bath with high T, so TH, and a cold bath of TC, T cold, then if these are both positive numbers, and we just think about this intuitively, we know that heat flows from the hot bath to the cold bath. Heat flow happens. And so if this is our hands, and our hand is a cold bath, and say the kettle is a hot bath, then we feel that the heat flows to our hand, and our perception is that it's hot. So if you have heat flowing to the cold bath, then it feels like a hot sensation. So now consider if I attach a bath to this high energy bounded phase space system, then assuming that this is not the same like energy as this one, then most likely, since this is the highest possible energy state, then heat is gonna, or energy is gonna flow into the attached bath. So energy flows from our negative T system to other bath. So then in this case, then we can go back to the normal temperature analogy and say, okay, if energy, or in other words, heat is flowing from the system to another system, then we must perceive this system as being hot. So negative temperature is actually hot rather than cold. And for part D, what about the case for infinite temperature? How's the system distributed among the states then? So infinite temperature, if we take the inverse of this instead of T, let's look at 1 on T. And 1 on T is equal to ds dE. Infinite temperature will correspond to a fixed point for this derivative. So this derivative equals 0. And this is positive on the left-hand side of this initial graph that we drew, and then it starts going negative after it got to this intermediate state. So this intermediate distributed state corresponds to ds dE is equal to 0, and hence corresponds to T equals infinity state. And this is the state where if you attach a bath to it, if it's colder, it might pump heat out of the system. But if you attach to a hotter bath, it'll like kind of get heat over there. So it's kind of like in the middle. So it's considered like a warm system. So it's not hot or cold. So this is when we kind of have to throw away our intuitive understanding of temperature, since it's not really sensible to talk about like infinite degrees as being warm. But yeah, that's it for this one. Okay, question 5, tutorial 4. So you have an ideal harmonic oscillator gas of m particles, and it's a neat approximation for sound wave in a solid. Given that the energy of a quantum harmonic oscillator, so they give it to epsilon n in a harmonic potential is h bar omega on 2 plus h bar omega n, where n is an integer that's larger than or equal to 0. So you can think about this is the ground state of your harmonic oscillator. And as you get more energy, you inject them in quantas of h bar omega, which is what basically quantum tells us. Okay, we need to find for part A the number of microstates given for a given microstate. So, okay, in this case, let's think about a total of m particles. And the macrostate for this system will be the energy, and we want to find the number of microstates corresponding to it. So I think there's a typo in the thing. It's for a given macrostate. So let's define the total energy of these m particles. Let's call it E. So this capital E will be like, could be written as, if I sum over all of the little n energy states, n equals 0 to infinity. So I like kind of iterate through the entire the energy ladder, and I asked how many particles are occupying level n. So this is the occupation number. Of state n, and multiply by the energy of that state. And if I add all of these together, then I should get the total energy for the entire ensemble. This is not infinity because we're not assuming this G is going to be non-zero everywhere. This G is probably going to be 0 past some point because we only have a finite number of particles. So if I rewrite this definition as subbing in this expression for epsilon here, then I get the total energy E is equal to n times the ground state, since every particle contributes ground state, so there just be a total n of them, plus by h bar omega sum from n equals 0 to infinity gn epsilon n. Oh, sorry, not epsilon n. I'll be n, gn times n. Yep. So rather than this infinite sum, I want to think about this slightly differently. So I want to write this as n equals n h bar omega divided by 2 plus h bar omega. I sum over a different index now, sum over index I, and I goes from 1 to capital N. So rather than summing through all of the possible energy states, I'm summing through all of the n particles. And summing through all the n particles, I just have to ask which state is that particular particle at. And these two are equivalent. You can convince yourself that. And I'm just going to call this thing capital M for like kind of simplicity's sake. So capital M is equal to sum of I equals 1 to n, ni. And that could be rewritten if I sub in like the inverse of this n. Like I rewrite this n as subject and I sub the rest of this in, I get sum of I equals 1 to n, total number of particles. The ith particle's energy divided by h bar omega minus a half. Or in other words, sum from I to n of all the particles' energy, epsilon I, is just going to equal the capital E. So it'd be the total energy divided by h bar omega minus n divided by 2. So this m is equal to essentially the total energy, and I take away the ground state energy. So this m represents all of the energy that's not used in the ground state to supply all the ground state particles. So now we can rephrase the question a bit. So the question is asking for a fixed total energy, capital E, how many ways can we arrange, how many ways can the particles, like microstates, be arranged? Or in other words, let's rephrase this now as, given m amounts of like non-ground state energy, given m energy bundles or parcels, how do we distribute it amongst n states? So this is a new question. So if you think about m like quantized energy bundles, I got like 1, 2, 3, 4, 5, 6, dot, dot, to the nth one, all these energy bundles. And then I have n particles that needs to kind of each hold some of this bundle. So then you can think about it as n minus 1 dividers. And it's like, okay, if I divide it here, then this first particle gets 1 bundle. So I equals 1 particle gets 1 bundle of energy. The second divider here, so then I equals 2 particle gets 2 bundles of energy. And I put another divider here, so I equals 3 particle gets nothing. And then keeps going like kind of I equals 4, here I equals 5, and blah, 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 until I put n minus 1 dividers amongst n bundles to decide how much energy each particle gets. So this is a very classic combinatorics problem of having like n quanta and n minus 1 dividers. So in that case, in total, we can move the bundles and the dividers. So they're both like individual choices. So our total number of choices from microstate omega of E and n number of particles is given by m plus n minus 1, the total number of choices, factorial, divided by m factorial and m minus 1 factorial. So divided by where we choose to put the bundles and where we choose to put the dividers. Yeah, so that's our expression for omega. And we're asked to find, and then later we're asked, for part B, we're asked to find the temperature as a function of energy. So to find the temperature from this, we just have to extract entropy from that. And then from entropy, we can get temperature from du, ds. So let's first try to get the entropy. So entropy will equal k log omega. Funky omega. Okay, and then this is just a lot of math. So if you just take the Stirling approximation, take the log and then Stirling approximation, all the factorials away, you get k m plus n log m plus n minus m log n, minus m minus 1 log m minus 1. So that's your entropy. And now for temperature, we're just gonna take the derivative. So 1 over T is ds d energy, dE. So in this case, we don't know what E is, but we know M is technically defined as energy. So we can do this as ds dm dE. The chain rule kind of thing. So ds dm would just be this whole thing is, close bracket. It's gonna be ugly, but it's not that ugly because half of these things depend only on n. And the ones depending on m, the logs will cancel out with the coefficient. So it's not gonna be that bad. So this equals k times log of m plus n minus log of m, and then all multiplied by dm dE. And I think I defined ages ago that m is, did I put it down? Yeah, m is over here. So sorry. So m is equal to So I defined previously that capital M is equal to E on h bar omega minus n on 2. So then dm dE, which is equal to 1 over h bar omega. So I take this into here, so multiply at the end, or 1 over h bar omega. So that's my 1 over temperature is equal to this thing. Yeah. Is that what we want to find? Yeah, the temperature. So that's fine. So T in terms of E is that. You can start back in the definition of M for E if you want this explicitly as a function of energy, but that's basically sufficient. Okay, so then for moving on to part C, we have to get the heat capacity. So we want to find CV, the heat capacity in terms of temperature. So for heat capacity, we need it's defined as dE dt. So that means we need an expression of the energy in terms of temperature. I think went all blurry. Okay, so we need energy as a function of temperature. So before we got 1 over T is equal to K log M plus N minus log of M times 1 over h bar omega. So we just have to invert this to get energy, or like M substitute back to energy, and then get that in terms of temperature. So yeah, if you sub back in the definitions, you get something this will look like K on h bar omega log of E on N plus h bar omega on 2 divided by E on N minus h bar omega on 2. I skipped a lot of lines of algebra, but it's not that hard. You just sub in M and then use the log laws. Okay, so in this case, if we take these to the other side, we get h bar omega on kt is equal to log of all this stuff inside. And now it's just simple taking exponential both sides and then solving for E. So you get something like E as a function of T is equal to N times h bar omega on 2, the ground state, plus h bar omega on E to the h bar omega on kt minus 1. So you get this like distribution function like term, the ground state energy, and that's your energy in terms of temperature. Again, I skipped a lot of algebra here, but it's just taking the exponential both sides and then expanding this out and then solving for E is not that difficult. Okay, now that we got the expression for energy in terms of temperature, we can find C quite easily. So C is just dE dt. So taking this differentiate with respect to T, then you get like a cosh function, n h bar squared omega squared divided by 4kt squared, 1 over hyperbolic cosine of h bar omega on kt.
Sure.
Yep.
Why is the heat capacity dE over dt rather than dQ over dt?
Because in this case, like, the energy, you can probably relate the energy to the heat exchange. Right, I didn't actually think about that. Okay, I'm guessing the energy in this case is like talking about the kinetic energy your particle have inside a potential. You're not talking about potential energy here. So the kinetic energy on average, like kinetic energy conceptually is like kind of heat in a sense. If you're able to give kinetic energy to something else, you give heat to something else. So that's like a kind of analogous expression. Yep. Nice. Okay, so last part, part D. Part D, you want to find the probability of finding a particular particle in the end state. Actually, I'll keep this divider thing because that's useful for this part. So we had n quantas of energy and n-1 dividers. If we want to find a particular particle in the nth energy state, so epsilon n, so find one particle here. That means we now only have n-2 dividers to play with because we're fixing one of the dividers for this particle. And then we're, depending on what energy n this is, we also only have now capital M minus little n number of bundles to assign because n amount is fixed for that particle. So I'm free to like fiddle around with all the other particles, all the other dividers, all the other particles, and how much energy all the other particles get. All I'm requesting is that n amount is fixed to this one particular particle, and then you can shuffle everything else. So now the number of microstates that corresponds to having one particle fixed is just kind of combinatorics of these two things left. So omega of like the fixed particle is equal to n, was it n minus n, n minus n plus n minus 2 all factorial divided by n minus n factorial n minus 2 factorial. So it's the same before, except I just subtracted off this little n and an additional divider. And now to find the probability of this n state, you have to invoke like the fundamental postulate of statistical mechanics is that each microstate occurs with the same probability. So that means if I just take the amount of microstates for this fixed arrangement divided by the microstates for the total system, then this ratio should tell me the probability because each one of the individual microstates have equal probability of happening. So like, yeah. If this fixed amount, this n goes to 0, then this whole thing goes to 1. So it's saying that it's definitely probable for you to find a particle somewhere. So in this case, we sub in what we had before. So we get m minus n plus n minus 2 factorial divided by m minus n factorial n minus 2 factorial. So that's the fixed one, and I have the total one that's inverted. So I get m factorial n minus 1 factorial divided by m plus n minus 1 factorial. Okay, so now if I take the limit that n is incredibly large, so then n minus 1 is basically n, n minus 2 is basically n. So I just ignore all of these little numbers around. Then I get m minus n plus n factorial m factorial n factorial divided by m minus n factorial n factorial m plus n factorial. So just this equation, but with all the little numbers taken out. So this n factorial cancels out with this n factorial. So we're left with just this expression. And this makes sense because if you just take, if you just do a sanity check, like if I take the limit where little n goes to 0, so I don't fix a particular particle, then this goes away, this cancels with that, and my probability is equal to 1 in the limit of that. So this expression is not doing anything like unexpected. Yeah, that's it for this one. Okay, and the rest of tutorial 4 are basically different contextualized variations of this question. So I'm not gonna go through those. I have a lot of time left anyway. See if we can do at least one question from tutorial 5. Okay, yeah, let's just do question 3 from tutorial 5 and call it a day. Okay, so question 3 from tutorial 5 asks, what is the heat capacity of a system of monatomic point particles only held together by gravity? So we have a bunch of monatomic particles floating around, and the only attractive force between them is gravity. So here, we know the interaction energy, or the energy between the particles due to gravitational attraction, is given by the kinetic energy plus their potential energy. But because they're a gravitationally bound system, and that's the only force involved, I can invoke Virew's theorem. So Virew's theorem tells me that the potential energy is equal to minus 2 times the kinetic energy if they're like a gravitationally bound system. So putting that into here, we see that the total energy is given by minus the kinetic energy, or the average kinetic energy. And then using equipartition theorem, I can write this as minus F on 2 KT. Yeah, I forgot an N there, NKT. Okay, and then again, we use the dE dt as the expression for heat capacity. Then this would just be minus F on 2 NK. So this might look a bit weird because you have a negative heat capacity. But for a gravitational system, it's not that strange, because if you imagine a planet that's orbiting closer to the central star, so it's got less energy, it doesn't have a lot of energy to run away from the central star, but then it's actually going faster. So closer orbits orbit faster. So if you inject kinetic energy, you end up losing total energy by going closer to the star. And another example is black hole physics. So in black hole physics, you realize that as the black hole accretes more mass, so it either sucks in other stars or planets or any other energy. So as it sucks in mass and energy, the temperature of the black hole actually decreases. And this works the other way as well. A black hole that's emitting a lot of Hawking radiation, so the black hole that's dumping energy out into surrounding, gets hotter and hotter, so it starts like evaporating faster and faster until the black hole completely evaporates. So in this case, the negative heat capacity describes this phenomenon quite well. Yep, and for part B, similarly, find the entropy for this. So, okay. So we're considering that our particle is bounded in some volume that's 4/3 pi r cubed, and I have a total mass m inside this volume, and the energy is given by still F on 2 nkt. So from the ideal gas, so saying we can assume ideal gas equation of state. So from ideal gas, we know the entropy is given by, what's it? NK 3/2 log of T plus log of V plus some constant from integration. So in this case, T is equal to E divided by NK times 2 on F. And then V is just that. I don't know how to rewrite it. V is just 4/3 pi r cubed. So putting these two in here, I get NK. What do I get? NK 2/3 E on NK 4 pi third 2/3 times by r squared. So it's combine these two with log laws, take this power there, and combine these two, and then sub in these equations, and then get some simplification. But yeah, this is the thing you get. And from that, we can separate out the ones that actually matter. So I get NK times log of E times r squared. And then put all the rest of the number together. So plus like NK 3/2, there's a 3/2 here as well. NK 3/2 log 2/3 or 3 to the power 2/3 1 on NK. All this junk. There's plus C and plus C. So this is all just a constant number, and so is C. So now I'll just recall this whole thing plus C bar, some other integration constant that I don't really care about. But this is the main expression for the entropy. So given an energy and how big the balance system is, you get this kind of entropy. Okay, then that's it for today. Any questions? All good. Then we'll see you guys next week. We got a break next week, and then week 7.